Good afternoon, ladies and gentlemen. My name is Mikio Nakahara, and I'm honored to be here today. First, I'd like to thank the organizers of Quantum Korea for the opportunity to introduce IQM and share our work with you. Let me introduce IQM in numbers. IQM was founded in 2018. Today, there are more than 320 employees with more than 125 PhDs. We have built more than 30 systems and delivered more than 10 systems to the customers. We sell on-premises quantum computers and offer cloud service as well. This is a list of on-premises quantum computers we have delivered and will deliver soon, up to 300 qubit QPU processor. In Korea, Chunbuk University has installed our quantum computer already. We produce two types of QPUs, one in crystal topology and the other in star topology. Star topology QPU offers all-to-all connectivity, which is important for some quantum error correcting codes. Both QPUs are equipped with tunable couplers, so you can control the coupling between two qubits as you like. Today, I'm going to concentrate on our approach to FTQC. The current quantum computers are called NISQ computers. Although no error correction is built in, it has many interesting applications such as optimization, quantum machine learning, and simulations. However, quantum error correction is essential for some important tasks such as prime number factorization. I think I don't have to spend a lot of time for fault-tolerant quantum computing. I think many of you are already familiar with FTQC. So what is important for FTQC is, of course, quantum error correction should be built in. I use this well-known symbol, NKD. N is the number of physical qubits, and K is the number of logical qubits, and D is the code distance, which means one can correct up to the integer part of d-1 over 2 errors. And we want to have the smallest number n for given k and d, or we want to have the largest k and d for given n. And to make sensible error correction, the physical error rate must satisfy some inequality. The error rate should be less than some threshold. And also, the logical gate operation must be executed in encoded qubits. And also, the real-time error correction. Real-time error correction and decoding are possible. This is the list of quantum error correction papers published by IQM. You can download these papers from our website, which also lists other IQM papers. And this is the website showing these papers. The simple error correction is repetition code. This is the classical error correction code. The simple one is just repetition code. You encode 0 as 0001 and 11. But this is not very efficient. And what is more interesting is LDPC code, which we are interested in. In LDPC code, you can encode many logical qubits for a given number of many logical bits with physical bits. This is the example of LDPC code. And let us and this is generalized to qubit quantum error correction. So this is a simple repetition code. 0 is encoded as 000, and 1 is encoded as 111. But this is not efficient, as I mentioned. And what we want is we want to encode more logical qubits with a fixed number of physical qubits. And so we copy the idea of LDPC code. That is called quantum LDPC code. So this is a quantum analog of LDPC code I mentioned. It is characterized by each stabilizer involves a small number of qubits, and each qubit contributes to a small number of stabilizers. And in the IQM example of this LDPC code are color code with code number 422 and variant bicycle code. And we did experimental demonstration for the first one, and we have a theoretical proposal for the variant bicycle code. This is a well-known surface code. You can encode 1 qubit with a large distance. For instance, in this case, we use 24 physical qubits to encode 1 logical qubit with code distance 4. But this is not very efficient. It can encode only 1 qubit, logical qubit. So in this paper, we introduced 422 coding. 422, the code distance is 2, which means we cannot make error correction, but we can make error detection. So we know that there is some error, then we just discard this calculation. So this is like in the classical case, if you have you encode 0 as 00 and 1 as 11, you can detect, if you check the parity of this the encoded bits, if it is 01 and 10 or 10, then you can detect that there is an error. Then you discard this calculation. You cannot make correction. You cannot tell which bit suffered from error, but still you can tell there is an error. So you just discard this calculation. In the same way, this distance 2 code doesn't tell you which qubit suffered from error, but you can say there was an error. And so this is the error correcting code we implemented in experiment. So we use this 6-qubit QPU, which are all connected. All qubits are connected through the central resonator. So this is an all-to-all connectivity. And these 4 qubits, D1 to D1, D2, D2, D4, D3, D4, they are used for encoding the qubits. And AX and AZ, they read the stabilizer. Stabilizers are XXX and ZZZ. And AX reads this X stabilizer, and AZ reads Z stabilizer. And this is a quantum circuit encoding and decoding this error correcting code. So you see these 6 qubits are connected to, all of these 6 qubits are connected to each other through the central resonator. And then after this experiment, it was shown that logical error per cycle was observed like 0.25% to 0.9%, 91%, depending on the logical state. And the best observed logical error rate is significantly below the physical CZ, control Z gate error rate of 1.05%. The logical lifetime exceeded those of the best physical components, showing that the error detection cycles improved coherence. The other work I'm going to introduce here is a variate bicycle code, which are published, uploaded in the archive in these two papers. And there is LDPC code called good LDPC code. That is kind of ideal one. But implementation of this ideal error correcting code requires many physical constraints, which is not very easy to access. So instead, we propose this variate bicycle code, which has the 72 physical qubits, which encode 12 logical qubits with code distance 6. And what is good about this variate? The code is the stabilizers involve distant qubits. What is the physical requirement is the demanding requirement is that it involves the stabilizer with the involving distant qubits. And in the crystal topology, this is disadvantageous, but compared to surface cores. But however, this is not a problem for free connected star topology. That is why we are interested in star topology QPU. This is a roadmap of our QPU. We produce two types of QPUs, as I mentioned in the beginning, the crystal topology and star topology. And in 2027, we will choose one of these possibilities. And depending on which quantum error correcting code we should implement. So this is a summary. High fidelity encoding of 2 logical qubits using the 4222 code has been experimentally demonstrated. The star topology QPU enables efficient error correcting circuit thanks to all-to-all connectivity. The variate bicycle code allows for encoding many logical qubits with a limited number of physical qubits, while also enabling large code distances. This implementation benefits from the star topology QPU. Depending on the progress of quantum error correction, we choose crystal topology or star topology. And contact me if you have any further information on the questions.